the pharmacological agent, the distilled form of it in medication form, is oftentimes going to be more effective because it is the distilled version of a chemical. But then it's also been studied, so there's a little bit more understanding about how it works directly and what the off-target effects of it are going to be. So to answer your question, I don't know about that one in particular, but there are versions of homeopathic medications for almost every class of drug, actual pharmacological drug that's out there. So you just have to be a little bit careful with homeopathic remedies and those supplements because they also don't have to be vetted by the FDA. So they could have off-target effects that interact with other medications that you take that might not be understood or have been studied.
Yeah, I think I'll stick to the Western medicine. I was just curious as far as like if it acted the same way or similarly.
I mean, there are some out there that do that. I just don't know the one-to-one correlation for what would be the best homeopathic anti-anxiety.
Got it.
All right, so that's one group of compounds there. Let's move along to depression, because if you're depressed, there's a pill for that also, right? So you're anxious, pill for that. Depressed, there's a pill for that. Actually, there's multiple pills for that, right? So here are some of the common ones that you may or may not have heard of before. So Prozac has been around for a long, long time. Zoloft been around for a long time also. Do you guys ever see commercials for these things?
Yeah.
Everyone seems to be happy.
Well, they're trying to sell you a medication. So not to get off topic here, but wait 1 second. Let some people in. The ability to create commercials create commercials for medications and for drugs is almost exclusively unique to the United States. So if you go anywhere else in the world, it is not legally, you are not legally able to create drug commercials that are direct to consumer drug commercials, right? Because essentially you're selling drugs like a product. And by and large, if you watch a drug commercial, they never really tell you what the drug is for. Here and there, obviously, if it's a very, very direct type of drug, like for depression, it'll say it's for, depression. But there's very, very little information, and it's always ask your doctor if this is right for you, So drug commercials actually are sort of not all that beneficial. And you only find them in the United States and also one other country. So they're also not against the law in New Zealand. So figure out why that's the case. And I have no idea. But the U.S. is one of the very, very few that allows for direct marketing of drugs. So be careful when you're a doctor that somebody's going to come into your office and say, I want to take this because I saw a commercial for it. Okay, so Prozac, Zoloft, Paxil, all the antidepressant family. Okay, these obviously have a mechanism and hopefully an understandable mechanism. So depression medications typically are going to fall into a group of medications that are known as SSRIs, which are selective serotonin reuptake inhibitors. Okay. Tell me, since you guys understand how this works, tell me how they are operating.
Are they blocking certain channels at the end of the presynaptic vesicle? At the end of the presynaptic cell, and they don't let serotonin get taken back up after the signal is complete?
Correct. Yes. Okay. So just by reading the name of it, right, that basically kind of tells you what it's doing, right? So it is selectively identifying and targeting the serotonin reuptake transmembrane transporter, which is known as SERT, so serotonin transporter. And that is, as you inhibit that, right, what it looks like basically is this. So in the presynaptic terminus, you have vesicles that are secreting serotonin into the synaptic cleft. And if you can insert a drug there that's going to block the reuptake back into the recycling mechanism, back into the presynaptic neuron or terminus, then ultimately what are you doing? You're leaving the chemical messaging system in the synaptic cleft for a longer period of time, right? Now, granted, some is going to diffuse away, but the length of time is going to be proportional to how frequently the molecules of serotonin are going to be able to access the postsynaptic ligand-gated ion channels, the receptors on the postsynaptic cell, right? So if you're stopping this this recycling mechanism, right, then ultimately what you're doing is just lengthening the amount of time that signaling can happen. And so if there's more serotonin left in the synaptic cleft, then ultimately that's going to induce more signaling in the postsynaptic neuron, directly based on the serotonin signaling, right? And so if serotonin clinically is a lack of serotonin or a lack of serotonin signaling, then a good way to modulate that is to increase the amount of serotonin signaling, right? And so the end result being that people who are depressed then feel a little bit better, right? Because serotonin is basically tied to how your mood works. All right, so that is one big group of drugs out there. There are also there's another family of drugs that does basically the same thing and targets, not mechanistically the same thing, but the same end result goal, targets the recycling mechanism, but from inside of the presynaptic neuron. Those medications are called MAOIs. So can anybody posit a guess as to what MAOI stands for?
Something antagonist.
Not an antagonist, no. So
Inhibitor?
Membrane.
So think back to what we talked about from recycling mechanisms, right? Did I tell you about an enzyme that does some recycling?
Oh, something oxidase.
What is the something? So we got the O part, oxidase.
Monoamine.
What's that?
Monoamine oxidase.
Monoamine, right? So single amine oxidase, and so those are enzymes that recycle monoamines like serotonin in the presynaptic neuron. So if you take a MAOI, monoamine oxidase inhibitor, you are effectively inhibiting the activity of that enzyme, and the goal of that enzyme is to break down compounds like serotonin. So effectively, you're getting the same outcome, right? You're increasing the amount of serotonin available in the presynaptic neuron, and therefore, when signaling happens, you get more efflux of that serotonin. So those are the two main categories of depression medications, SSRIs and then MAOIs. So those are effectively just kind of playing around with serotonin levels. And as long as you're playing around with serotonin levels, that's going to evoke some sort of change within your mood, right? So if you're depressed, you can hopefully modulate that and feel less depressed, whatever that means, right? Perception is unique, right? So what is depressing for one person is not depressing for another person, which is also why brain chemistry is hard, because there's not one specific outcome, because nobody knows what perception actually is, right? So I could tell you that something is the color blue and you tell me that it's a color purple. Well, we perceive things differently, right?
You might need another drug. You can't change how people perceive color though, can you?
You can actually. So
with the glasses, right?
Actually, a couple of years ago, not with the glasses. I'm thinking about there was a big to do, maybe about, I don't know, I want to say like 10 years ago, maybe, about a dress that was shown on TV, and some people thought that it was the color white and gold, and some other people thought it was the color blue and black.
Oh, I remember that.
And
I remember that.
Yeah,
That was such a big thing.
right. And so that ultimately shows you perception, right? So something that should be as objective as color sensation or color perception is subjective, right? So some people can look at something and say, well, that looks gold and white to me. And some people see that and see it as blue and black. It's just how your brain is processing information.
Was that like 50-50 split between how people perceived it, or was it more skewed?
The actual numbers, I don't know. I'm not sure if anybody, did an actual study for that. I think it was more anecdotal that people would just kind of comment that I see this or I see that. But from a cognitive perspective, that really underscores the fact that perception is a unique phenomenon for every individual, I want to say person, but ultimately every individual organism. So the way your brain is wired and the way it signals is a very unique phenomenon for every person. So take that into account when you start considering how the brain works and how drugs modulate the brain, because ultimately the outcome for one person with the same medication, with the same affliction, is not going to be the same outcome for another person with the same affliction. All right, so since we're talking about serotonin here, it is worth just bringing us back to something that I mentioned during the lecture, which is the reward system in the brain. All right, so if you delve into a neuroscience class, you'll go into this. This is very, very complex. So the brain is a complex organ, as you would imagine, right? And very little is understood about, maybe only recently, more and more is becoming understood about how there are groups of neurons that make neural networks. And so there are regions of the brain, even though a region is not a defined thing that you can look at, it's just an area that has a population of neurons, which might not be all that distinct from a neighboring section, but there are regions of the brain that have groups of neurons that act together, right? And so those are called pathways or tracks. And some of the more studied tracks and groups are going to make up what we're looking at here, which is the reward system of the brain. So the reward system is tied to a number of different areas, which again, I don't want to get into like all of the specifics of it. All I want to kind of get across to you is the two main populations of signaling neurons that are going to be secreting different neurotransmitters, in particular dopamine and serotonin. Okay, so the blue arrows, so dopamine comes from the midbrain, basically, and the midbrain also is going to be an area that's going to complex with your hippocampus and your amygdala. So this is going to dopamine signaling ties to how you perceive feelings, how you generate memories, and all of the other functions that you see down below. So dopamine signaling is going to then also be processed by your frontal cortex and create for you most of the compulsive behaviors that get assigned to dopamine signaling, right? So why do you become addicted to certain things? What is the motivation of a reward? So we talked about reward signaling previously, and I had mentioned that it basically is derived from dopamine signaling. And just to point out here, motor function, right? So this is one of the more physiological roles that dopamine has to play, that it's a fine motor coordinator. So you do need signaling of dopamine, not just for the reward system, but you also need it for some physiological activity as well. So the dopamine signaling that we are talking about typically comes from what's known as the mesocortical pathway. So that is the midbrain, where you see the origin of the blue lines, and then the cortex, right? Usually the frontal cortex, because that's where you think. That's where your cognitive reasoning and thought processes usually unfold. That you're aware of, and so a lot of dopamine signaling has to do with the perception that something is beneficial or something is good, and then that leads to the ability to think that you want to do that again and to pursue that activity again. Okay, and then there's other dopamine tracks that we don't have to get into. If you follow the red lines, notice that the red lines also come from the mesolimbic area, and the red lines don't just make their way into the frontal cortex, but they have locations and receptors that are found throughout the different regions of the brain. So different physiological areas that are governed by different regions of the brain. So if you go all the way to the back of the brain, some of the areas in the back of the brain govern physiological activities like vision, right? So the visual cortex is all the way in the back of the brain above the cerebellum. So you can see that there's a lot more signaling that can happen with serotonin, the red line, as opposed to dopamine. Dopamine is really a motivating type of thing. And serotonin has more to do with a global signaling that will affect a change in your whole physiological state, as opposed to dopamine being more of a motivational type of signaling molecule. All right, so that's where, if you take a look at the red track, that's why serotonin has more to do with mood, right? Your whole physiological being. How do you feel about this, right? How does your body feel about that? How do you think about that? What's your perception of this? And that's also why it has to do with some of these more autonomic functions like sleep and your hunger cycle and your thirst cycle and things like that. So serotonin is a more global kind of signaling molecule tied into the reward system. And then dopamine is more of a direct activity, reward driven type of signaling. All right. So why am I talking about this? Not necessarily to get us mired in the details about the brain, but more to understand when you look at changing the levels of neurotransmitters, why you get the kind of common outcomes that you see with given classes of drugs, right? All right, so that was true in pharmacological agents like depression medications, but it's also true in the utilization of illicit drugs as well. All right, so enough about pharmacological agents. Let's talk about real life here. So real drugs. So let's start with when I say real drugs, I don't really mean real drugs because these aren't real drugs, but anything that's a chemical could technically be a drug. So what's our gateway? Our gateway is usually smoking and drinking, right? Nicotine and alcohol. All right. So as you would imagine, and as I'm sure everybody is aware, both nicotine and alcohol are addictive substances, right? So they have to, in some way, shape, or form, be targeting your neural chemistry and augmenting that somehow. So how does that work? Okay, let's start with nicotine. So nicotine binds to acetylcholine receptors in the brain. Now, I mentioned acetylcholine as a participant in one very specific activity. And I mentioned that there are other receptors in the brain that are used for other targeting or other signaling, right? And this happens to be one example of it. So those receptors are literally called nicotinic receptors because nicotine binds to those receptors very effectively. So where did we see these receptors before, as far as review is concerned? So what is acetylcholine?
This? Oh, okay. I think you meant like
a neuromuscular junction.
Okay, so just to bring us back to using this as a review a little bit, acetylcholine is the main neurotransmitter that's going to evoke muscle contractions, right? So we saw that then at the neuromuscular junction, right? So this is the signaling that happens from motor neurons to affect a change in skeletal muscle and get the muscles to contract. All right. Now that's all well and good. You could use acetylcholine for that, and that's predominantly what it's used for. But there are other ways that you can use the same molecules and the same receptors and then just have different circuitry and different signaling unfold. All right, so lucky for us, the nicotinic receptors are found on dopaminergic neurons. And so those neurons, which feed into the reward circuitry, are being triggered by the binding of nicotine to nicotinic receptors on these neurons, right? So you're effectively just pushing the signaling through neurons that are basically designed to create dopamine. Also, I keep saying you might have picked up that neurons get classified as some term and then ergic at the end, right? So that basically is just identifying what the neuron makes. So GABA creating neurons are called GABAergic neurons. Dopamine creating neurons are called dopaminergic. Serotonergic neurons make serotonin. So that's if you get into neural chemistry, you can start identifying what a neuron does, and then you kind of call them by certain names based on what they make predominantly as far as neurotransmitters. All right, so if you are inducing signaling with dopamine, then obviously you are going to be engaging the reward system, and dopamine is going to cause a perception that something is positive and beneficial to you, and that's ultimately where the addictive quality of nicotine is going to come from. All right, so as you activate the neurons, you're going to secrete more dopamine, right? And then that's going to be perceived in the reward circuitry of your brain. So hey, that felt good. Let's do that again, right? So that's nicotine, and nicotine is, because it's engaging the firing, right? The excessive firing of these neurons. Would you consider nicotine to be an excitatory type of compound or an inhibitory type of compound? Excitatory, exactly. So that's why nicotine is categorized as being a stimulant, right? So stimulants basically just induce more neural activity. It's also worth mentioning that nicotine will affect your adrenal gland as well. So nicotine will induce the secretion of adrenaline or epinephrine, and that what does that do? So specifically in your blood system or your circulatory system, what does epinephrine do?
In your blood system, vasoconstrict.
Right, vasoconstriction. So if you smoke for long periods of time, you'll find that people who smoke for years and years and years oftentimes also have very high blood pressure, and that is an off-target effect of nicotine with this low-level secretion of adrenaline that occurs because of that, and oftentimes you get these kind of secondary pathologies that come from chemicals and compounds, not just the main reason for why somebody would take the chemical. So I guess that's worth mentioning here too. All right, so let's hop over to alcohol. So alcohol is interesting because alcohol will disrupt the balance of GABA and glutamate signaling. So it doesn't have one specific mechanism by which it works. It doesn't like target a receptor here or target a receptor there. It basically just, in very generalized fashion, will reduce excitatory signaling and will increase GABA signaling, right? So you're reducing all the excitatory messages, you're increasing all the inhibitory messages, okay? Now think about a drunk person, right? Does that drunk person seem like they're they have a lot of neural activity or very reduced neural activity?
Reduced.
Probably reduced, right? Drunk people usually don't really know what's going on, and a lot of that reduction in activity leads to some of the outcomes that you would see with excessive alcohol consumption, like when people say that they black out and they don't remember anything. Okay, the reason why you don't remember anything is because you basically turned off all of your excitatory signaling, and you don't have the neural arousal to be able to generate memories or to think clearly about an activity. So basically alcohol just kind of mucks around with the balance between those two signals. All right, so you inhibit glutamate signaling, less excitation. You increase GABA signaling, more inhibition. And so that's why alcohol gets categorized as a relaxant, because it basically is increasing inhibitory signaling. So the result then is that you get very, very diminished excitatory signaling and increased inhibitory signaling, and that effectively is like an anti-anxiety medication. All right, so people will drink to calm their nerves, right? That's something that's kind of a classic kind of excuse as to why somebody has to have a drink before they do something that's an anxiety-laden type of event. Well, I got to calm my nerves a little bit, so I'll go have a drink. All right. Luckily, it also induces dopamine signaling in the brain, right? So again, not with any specific direct mechanism, but it increases the dopamine release from those neurons and engages the reward circuitry, right? So going back to what I said before, alcohol is also addictive, and the addiction comes from the engagement of the dopaminergic pathways within the reward system. Also worth mentioning that alcohol will disrupt your ADH hormone level in your body. So it actually decreases the amount of ADH that gets secreted. So somebody tell me what that does.
Low blood pressure?
So less about pressure and more about fluid retention.
So you'll pee a lot.
Exactly. Okay. So if you reduce ADH, right, that is the signal that allows you to retain fluid in your body. So if you're stopping that hormone from being secreted, that ultimately is going to increase the amount of fluid that is going to be expelled from your body. So to a little degree, you could make the equation liquid in, liquid out, right? So the more you drink, the more you got to pee. But it also is interrupting your hormonal signaling, and so it's inducing the efflux of liquids through your kidneys. So that also increases the amount of bathroom frequency that you'll see when you begin drinking mass quantities of alcohol. All right, fun, right? Okay, so drinking, smoking usually leads to other recreational activities. So let's talk about the next step in the game, which is usually weed, right? Cannabis. What is the main psychoactive part of weed?
THC?
THC, right. Tetrahydrocannabinol. So that is the main component of what cannabis actually is, right? Otherwise, it's just a plant. But what people really care about is the chemical from the plant, right? This goes back to what you said about homeopathic medications. So this is a good example of, a plant-based chemical that can be refined into pill form, and obviously there are versions of it that are capable of being actually used in pill form. So there are marijuana or THC-based medications out there. All right, so these target what are known as cannabinoid receptors. So what do you think cannabinoid receptors in your nervous system are used for? Perception. And of course, perception is going to be unique to everybody, right? But what is the smoking of weed evoke in people who are doing that?
I mean, they usually become
why would you use it?
Like more mellow.
More mellow. Okay. So it is, how about from a medical standpoint, right? So what's the whole rationale of legalizing marijuana, right? From medically, what do people say that marijuana is used for?
Pain relief.
Pain, yeah.
Pain management.
Stress relief.
Right. Okay. So, well, medically, not really stress release, but, wait, what? Somebody saying something?
Yeah, I also heard that it's like it makes you hungrier. Well, yeah, it does. So it like gives you the munchies or something like that. And then like
right. I don't know. I've only heard from people that it gives you the munchies. I don't know. Yeah, so it's so from a perception standpoint, there's two different classes of the cannabinoid receptor. There's a CB1 and CB2. CB2 is found in your body. CB1 is found in your brain, right? And they're going to evoke different different outcomes. So there's mood modulation, there's appetite modulation. Those are usually from the or the appetite is from the CB2 receptors. CB1 receptors are going to be for the mood modulation and then the pain perception modulation. All right, so pain is really the key from a medical standpoint about what weed is really all about, right? And why it's kind of now coming more into the mainstream as a medicinal type of medication. Okay, so the endocannabinoid system is a natural system in your body. Your body actually makes analogs of THC, and those are called endocannabinoids. So they're lipid-based molecules that target your cannabinoid receptors. So it is actually an endogenous pain system that you have in your body. And that synergizes with the opioid system. So I mentioned the opioid system previously. So when we talked about neurotransmitters, I didn't pick pain for no reason. I picked pain because I knew that I would cycle back around to it, right? So the pain modulation in your body has many different layers and many different systems that allow for a very fine-tuned leveling of what people perceive to be pain. And you have multiple different systems, not only just the straight signaling of glutamate and GABA to either induce pain signaling or reduce it, but then you also have these built-in hierarchical systems like the endocannabinoid system and then the opioid system that allow for much more fine-tuning for pain management from endogenous molecules. So with that said, what is the group of drugs that's targeting the opioid system? Exogenous drugs.
Opioids.
What?
Oxycodone.
I heard oxycodone. Okay, so that's one type of drug. So you could name a whole slew of them, right? So heroin, morphine, opium, oxycodone, hydrocodone, any of the derivatives of opioids, which really derive from opium itself, right? So this is yet another plant-based chemical that got refined over time and then got changed chemically into all these different forms. Okay. What neurotransmitter did we talk about that's really the endogenous form of this chemical?
Endorphins.
Endorphins, right. Okay, so endorphins are one class. So endorphin, remember, is called endogenous morphine, right? So that's where endorphin comes from. You also have other classes of molecules that are called enkephalins, endorphins, and then dynorphins are another group. So there are kind of three categories of these endogenous molecules that will target opioid receptors. And opioid receptors actually themselves come in a couple of different varieties. And the main one that gets used in the brain is called the mu receptor. So that's the kind of the strongest acting receptor. All right, so what other neurotransmitter here we talked about were the endorphins. That was what I brought up in class. And of course, the result is going to be the modulation of pain, right? So that ultimately is another system within the body that's going to be basically doing the same thing. Now, if you look at either one of these systems, right, they both are going to increase dopamine secretion, right? So specifically with the opioid system, we know that people get addicted to opioids, right? And so the activation of opioid receptors oftentimes from a region of the brain known as the VTA, which is called the ventral tegmental area. So that's part of the mesocortical reward system dopamine secreting circuitry. And that will be engaged with opium use or opioid use, and that ultimately will lead to dopamine secretion. The same is true with cannabis as well. So that induces dopamine secretion also. So these substances then also become addictive substances, right? So when we think about the legal forms, right? So heroin, morphine, opium, those are all illegal forms. And when I asked you guys what types of medications, you told me the more prescription-based ones, right? So things like hydrocodone, oxycodone, fentanyl, those are the or up until about 5 or so years ago, those were the acceptable opioid forms. Well, as long as you got a prescription for it, then you can't possibly be doing anything wrong, right? There's no way that you could abuse a prescription drug. So only worry about the people smoking heroin or shooting up heroin. Those and smoking opium. Those are the ones who are doing something wrong. But the guy working on Wall Street who's hooked on oxycodone, that guy's fine. So clearly there is a problem with the system, but it's something that you should be aware of because you don't want to be the doctor writing excessive prescriptions for these things.
I mean, so this, I was actually interning for the DA on Staten Island. And so we had like a really big issue. People like 10 years ago, like during the recession, people got hooked on like legal opioids. And then that translated to heroin. And we had such an influx of overdoses that we had to have Narcan training programs.
Yeah, it's actually it literally is a crisis that like nobody is talking about. The amount of Americans that are hooked on opioids, synthetic opioids, is astronomical. So you might not see it day to day, but across the country, this is actually a very, very large problem that almost nobody is dealing with. And certainly, given the last year that we've had with the pandemic, it's completely fallen by the wayside. But it is something that has to be corrected at some point. All right, so that is a step up in the drug usage. So if you start smoking weed, maybe it will lead to hallucinogens, right? So let's get recreational with this. So if you take a hallucinogen, the easiest gateway, I would assume, would be taking something like this. So these are mushrooms, right? So this would be possibly something you would stumble across at a party. Okay. So,
or a forest.
Or a forest, yeah. If you know what you're looking for, be careful because some mushrooms are poisonous. So make sure you know what you're doing. What's the ingredient? It's not actually the mushroom. We care about chemicals, right?
It's the psilocybin, I think.
I think, maybe. Yes, it is psilocybin. Psilocybin is the psychoactive ingredient in mushrooms. So the question is then, what's this doing, right? So we generally know what the effect of hallucinogens are going to be, right? You're going to hallucinate to some degree or another. So there's got to be some interaction with the neural circuitry. So what is the interaction? So the metabolite of psilocybin will act as an agonist of serotonin receptors. All right, so serotonin receptors are, the actual name for a serotonin receptor is called the 5-HT receptor. And that comes in a couple of different varieties, which, we don't have to parse out here, but there is one specific form of the 5-HT receptor that is the 2A version of that. And that typically is the one that is going to be engaged with hallucinogenic compounds. So essentially what you're doing is you're activating. So an agonist is an activator. This is a compound that's going to go off and target the serotonin receptor. Okay, and in addition to that, it's also changing the activity of excitatory and inhibitory GABA and glutamate signaling in your brain. Now, I would like to give you a more defined mechanism to this. And the reason why I can't is because very few people study these things, right? So when you get into illicit drugs and how they work, there's usually a general understanding of like, I think it's kind of like this, but it is very difficult in a research setting to get funding to just figure out how mushrooms work, right? So no agency is going to give you grant money to just go play with mushrooms, right? And here, see how this hallucinogen works, right? So unless there's a reason for it, unless you can tie it to a medical reason or research that is for like, some specific outcome, very, very few people are capable of doing research in this. And also the fact notwithstanding that it's a controlled substance, right? So the understanding of how these things work, right, mechanistically in your brain is very, very limited. So you could basically identify, well, the compound kind of looks like this, it kind of targets that. And we know if you're engaging serotonin receptors, then that's going to alter your mood, right? Now, the question is, yeah, okay, I understand that if you're on a hallucinogen, you're probably going to have your mood altered, right? But one of the key aspects to hallucinogens would be the fact that you hallucinate, right? So why would that be the case? And if you think back to what I told you about the reward system in your brain, remember the serotonin tracks really made their way around your whole cerebrum, right? And there are clusters of serotonin receptors in different areas of your brain. And one of those clusters is found in your visual cortex. And so if you're triggering these serotonin receptors, ultimately you have the possibility, and if there's differential triggering in the different populations of receptors, you're going to get different outcomes, right? And so if this happens to trigger the 5-HT receptors a little bit more effectively in the visual cortex, then you can make a rationale, or you could provide the rationale for why the perception is what it is, right? Why do you hallucinate? Well, you're probably triggering this group of receptors, serotonin receptors, a little bit more than they would be normally, and because of that, you're getting more activity in the in that region of the brain, and so that is probably where the correlation comes from. But like I said, mechanistically, it's a little bit more of a black box.
Do you think that'll change now that, like, I think Oregon didn't they like make every drug legal, including mushrooms, and I think in Colorado or in Denver also, like, it's fully legal, no problem. You think that'll change now?
I mean, just because you legalize things doesn't mean that people are going to take their time or money to study it, right? So, I mean, these things are legal in Amsterdam. You could just walk into a coffee house and buy mushrooms, and that's legal there, but that doesn't mean that people there in Europe are studying it anymore than they are here. So, if the outcomes are not dramatic as far as bad behavior, then there's really no reason to study it. So as long as it works and it doesn't kill people, or doesn't really degrade their life to a certain degree, then sometimes you can make a case just for legalization for recreation.
Right, and that probably goes back to what you said before, that like the homeopathic stuff isn't FDA regulated, so it's probably the same with this.
Right. Yeah. Be careful about. So the wall of quote unquote vitamins at a drugstore, 95% of that is unregulated. So, I mean, even when a company makes a pill, the amount of whatever it is that they say is in that pill is not regulated. So be very careful about vitamins and supplements, because they are not really medications. All right.
What about like bath salts? Is that the same as this stuff?
Bath salts. We'll talk about that in. Maybe no, we won't talk about that. But bath salts is that's a whole different class of medication. So I can only get so far with this, or not medication, a class of drug. So we can talk about bath salts another day. All right. So. All right. Mood and cognition are going to change, right? So that's why you would take a hallucinogen. Now, if you want to kind of put this in context here, you would find that hallucinogens really are not addictive, right? So tell me why it's not addictive.
People go through crazy experiences and they're scared.
It doesn't target dopamine.
Okay, so that's a better answer, not just the outcome answer. So you're not engaging dopamine, right? So by and large, you're engaging serotonin, and serotonin is not the motivating type of neurotransmitter dopamine is, right? So the addictive quality from drugs, illicit or prescription, comes from dopamine signaling, right? So that's where problems unfold when addiction starts to unfold. But serotonin, if that's engaged, that tends to be less addictive, right? So hallucinogens typically are not all that addictive, which is what makes them a little bit, quote unquote, safer and more recreational. All right, so there is very little dopamine involved in the signaling here and the outcome, the perception that you have. All right, so let's step up our game here with hallucinogens, right? What's the next level hallucinogen? I want a stronger hallucination experience.
LSD.
LSD. Okay, I want something stronger. I could take some LSD, right? And the same would be true of LSD, right? It's just a chemical, a synthetic form of psilocybin. Basically, it's going to presumably unfold in the same way. It's just generally more potent. Okay, can you think of another one that basically does the same thing? Also natural.
There's like a frog poison that Mike Tyson talked about on his podcast.
EMT.
EMT. I'm not sure if I heard about that.
It's D.
Oh, DMT. Oh, yeah, that I have heard of. Wasn't what I had in mind, but
would it be ecstasy?
No, not ecstasy. So hallucinogens. So LSD is very, very similar to a compound known as mescaline. So mescaline is sometimes known as peyote. So again, it's a powerful hallucinogen that comes from a plant-based source, and it effectively is going to evoke the same circuitry in the brain, right, leading to powerful hallucinations. So little bit of a black box with hallucinations and hallucinogens, but ultimately they're a little less, I don't want to say less regulated, but less worried about because they don't evoke the dopamine signaling that would lead to addiction. So very few people are addicted to mushrooms. All right, since somebody brought up ecstasy, who's up for a rave? What are we going to take? What is ecstasy?
Like an excitatory something like that, or cocaine.
Well, I mean, from a chemical standpoint, right? So, come on, I got my glow sticks, turning the techno on. What's the drug that I'm actually trying to take? So, in a pill of ecstasy is a chemical.
Maybe adrenaline, something. I don't know.
So the chemical in ecstasy is actually a chemical known as MDMA. Right, so MDMA stands for methylene dioxymethamphetamine. So really, it's the methamphetamine part of it that is evoking the outcome. Right. So how does ecstasy work, or more directly, how does MDMA work? Right. So got to be messing with your neurotransmitters, right? That's the whole point of this. All right, so let's think back to how your neurotransmitters work. Okay, the synapse in your brain, or between neurons, have transporters, right? And those transporters are capable of moving specific groups of molecules or specific molecules. And MDMA has a twofold effect. It will increase the amount of cytoplasmic biogenic amines, specifically serotonin. So it will take the vesicles, and it will vesicles have transport membranes. So there's something called a VAT transporter. And that's how you get amines into the vesicle, right? But you can also make amines come out of the vesicle also. So that's part of what MDMA does. So it gets the secretion of biogenic amines out of the vesicles, and then it allows for the secretion of those biogenic amines out of the cell, out of the cytoplasm, into the synaptic cleft. So it's basically just artificially causing secretion of biogenic amines. So that's one aspect to it. And then the second aspect to it is that it also will prevent their uptake, right? So the reuptake of it is inhibited. All right. Now, out of all of those biogenic amines, right, specifically serotonin, dopamine, and norepinephrine. So those tend to be the big three biogenic amines that you consider with reward signaling and drug circuitry like this. MDMA has the highest affinity for the serotonin transporter. Okay. And so the result of that, right, it's probably like, 15 times higher affinity for the serotonin transporter than the other two transporters. And so what happens is you get a secretion of a ton of serotonin into your synaptic signaling, synaptic clefts, right? So think back to what we talked about with depression medications, right? The whole point of serotonin is to keep the signal going, right? And that will counteract depression. So what this is doing is basically providing a very strong increased antidepressant for you. It is overwhelming the system with serotonin. And because of that, people who take ecstasy, which is where the name comes from, feel very, very good, right? So if this is a mood modulator, that ultimately is what the outcome is, what the perception is, right? Everything is great. This music is great. This feels great. That looks great. This tastes great, right? Everything is great. So that's just mood modulation. It's just, you increase the amount of signaling and now everything is great. Okay, so that's why people who take ecstasy have this kind of very broad-based modulation in how they feel, right? What their perception of feelings are, what their mood is, how they empathize with people, all of those different outcomes. What was the original use of MDMA? Does anybody know? So oftentimes drugs like this come from actual research and from a good place. So this was originally used as a marriage counseling medication. So for people who were having trouble in their relationship, they would be prescribed MDMA, and it would just make you feel better with the person that you're around. So it seemed to work, I suppose, good enough to make it be abused.
Didn't Freud experiment with all these drugs and hallucinogens as well?
Cocaine. He did a lot of cocaine. So
okay.
Yeah, we'll talk about that in a second. So this also, because we're talking about the secretion of these biogenic amines, this also increases norepinephrine secretion. And that's where, very much like adrenaline, right? So norepinephrine is noradrenaline. You get the same off-target effects that you would get from adrenaline. So this is why people who take ecstasy, why their body temperature goes up. So it's basically like you just have a rush of adrenaline. Right, so your metabolism goes up, your respiration goes up, your circulatory system is going to constrict, right? So that's all of the kind of secondary outcomes with MDMA, and that's what oftentimes, if it's going to be fatal, that's where the fatality comes from. It's the quote unquote overheating in the environment, and usually people who take this take it in situations where, in a rave-like situation where people are very, very tightly packed together, where it's very hot, where people are dancing a lot, sweating a lot, and that could contribute to the overheating and the fatality induced by the drug. So typically not the drug itself, but the drug in combination with the environment. All right, so that is MDMA. And since we're talking about methamphetamines, right? Let's talk about crystal meth, right? Yet another methamphetamine. So why is ecstasy recreational and crystal meth more dangerous, right? So there's a big question to ponder here. And the answer is neurotransmitters, right? Always boils down to neurotransmitters. So crystal meth is very dangerous. MDMA, a little bit less so, right? So if you compare the types of methamphetamines, they're going to work in approximately the same way. The only difference is what neurotransmitter are they targeting? And if you compare crystal meth to MDMA, the secretion amounts of the different biogenic amines get skewed slightly. So the inhibition of the transporter for serotonin is going to be targeted less so, but the inhibition of the transporter for dopamine and noradrenaline are going to increase substantially, right? So MDMA targets the serotonin transporter, leading to more serotonin signaling. Crystal meth has a 30 times more potent affinity for the dopamine transporter, right? So you get much more dopamine signaling, and it has a 60 times great affinity for the noradrenaline transporter, which means you get an excessive amount of adrenaline signaling, right? So how does that play out, right? So where MDMA makes you feel good because it's largely serotonin, in crystal meth, you feel good, or the rush really comes from the increase in adrenaline and the increase in dopamine signaling. Okay, and then the rolling back of the serotonin. All right, so when you can compare the two, right, the circuitry, the MDMA interaction versus the crystal meth interaction, okay, that ultimately leads to the long-term pathological outcomes of these things, right? So in the case of crystal meth, this is far less of a mood modulator like MDMA would be, and much more of an addictive type of substance. And that comes from the dopamine, right? So dopamine levels are sky high, and that's where the addictive quality of crystal meth is going to come from. All right, so when you have dopamine signaling, that's going to induce addictive behavior, and that's where the compulsion comes from, and the drive to want to do things again and again and again, right? There are also consequences to crystal meth, right? So if you've ever seen somebody who's hooked on crystal meth, they oftentimes have very classic kind of pathologies unfolding. So very much like this individual here, the quality of their skin is going to change. So that's number one. Number two, does anybody know what other kind of classic pathology you get with crystal meth?
You lose your teeth?
You lose your teeth, right? Your teeth rot. Okay. The same reasoning, or the pathologies are based on the same reasoning. And that reasoning is the wild increase of noradrenaline or norepinephrine. So what we know about adrenaline, right? We talked about this a couple of times. It will lead to vasodilation, right? And effectively what adrenaline does is it triggers your fight or flight response. And that's really for diverting resources to core areas of your body that should be engaged in either a defensive mechanism or primarily a defensive mechanism, right? Fighting or running. So what you get over long periods of time with very high levels of adrenaline is going to be situations like this. So it will divert blood flow from places like your salivary gland. So your mouth becomes very dry. And because of that, you don't wash away the acids that are being produced by the bacteria in your mouth. And so that leads to tooth decay, very rapid tooth decay. It also is diverting blood flow from your skin. And so that's why skin tends to become like very dry and scaly and patchy, and will also induce sores like you see. So this is long-term effects from crystal meth use, which is really just tied to excessive epinephrine signaling or norepinephrine signaling. So crystal meth is not good. Stay away from that. All right. Speaking of addictive substances, cocaine. So you brought up Freud, right? He was a big cokehead. So, or I guess if you prefer, you could have some crack. So does anybody know what the difference is between coke and crack?
Crack's like the liquid stuff they put on a spoon, right?
Well, you make it liquid by putting in this. You have to like
when you cook it, right?
Is what?
It's like when you cook it on like a spoon or something.
Well, so you're focusing more on the delivery mechanism. But both are powders, right? Or they begin as powders. And so what crack is, so it's called crack cocaine, right? So they have to be related somehow. So crack is actually just a mixture of cocaine and some sort of base. And that base tends to usually be baking soda. So you mix the baking soda with the cocaine, and then you process it into more solid form. So crack tends to be like rocks, and obviously it's harder to ingest rocks, right? You don't want to just eat it. So that's where the whole spoon comes in, right? So you take crack rocks and you put it on a spoon, you heat it up, you need a lighter, and then that's ultimately where how the crack gets delivered. Because of the processing, it also is very much has a shorter effect in your body too. So anyway, so cocaine, right? Cocaine obviously can only be snorted with a $100 bill. And if you begin using cocaine, cocaine is yet again going to be modulating your neural circuitry, right? So cocaine is going to affect the same exact biogenic amines, right? Dopamine, noradrenaline, and serotonin. The only difference here is cocaine is going to target them differently, right? So is cocaine addictive?
Yes.
Yes, cocaine is wildly addictive, very, very addictive. And it is addictive because of what? So what do you think is the main amine here that we're talking about?
Dopamine.
Dopamine, yes. Okay. So dopamine.
Is that ironic? Dope, cocaine?
Well, I think that's just a coincidence. All right. So what cocaine does is it will prevent the reuptake of dopamine. It is an exceedingly powerful anti-reuptake of dopamine. So that's number one. You're just leading to excessive dopamine signaling. But the potency of cocaine actually comes from the reorganization of those neurons. And so the secondary effect of dopamine is the fact that it reorganizes dopaminergic neuron circuitry in your reward system. So not only is it leading to more dopamine signaling, but it's also causing it's almost like learning, right? So the same way that we talked about strengthening neural pathways, cocaine basically has that effect. And so you get strengthening of the dopamine signaling in your reward system. Okay. And so that's what positions cocaine as being one of the most addictive substances that people can take. So if you've learned anything about this, then I would hope that it would be that you should stay away from cocaine, because that will be kind of opening a Pandora's box. And that's also why Freud was addicted to it too. All right. I believe I'm out of time. So that is that for today. So enjoy your spring break. Don't do drugs, and we'll pick up in a week from Tuesday. All right, guys.
Have a nice break.
Thank you, Professor. I thoroughly enjoyed today's concept review.
This was one of the best.
I'm glad you learned something.
Have a nice day, Professor.
Don't do drugs.
Of course,
Thank
of course.
Thank you, Professor.
All right, guys. Take care.
Thanks, Professor. Have a nice break.
You too.
That was definitely one of the top concept reviews.
Well, it's hopefully will help you understand what happens out there in the in the nervous system. So I'm sure you'll revisit this again somewhere down the road in some pharmacology class.
All right. Thanks again. Have a nice week.
All right, guys. Take it easy.